Okay. Yeah. Okay. So anyway, like these things we know from for the discrete case, right? So the expectation of a discrete random variable is given like this, and so here I have written expectation of g of x, which is g of x itself, and then we have the PMF of the random variable x. Okay, so this is the case for the discrete case, and you know that in the continuous case we have to replace the sum by the integral, and then we have to replace the PMF by the PDF. Okay, so that's what we are going to do. So by changing the sum to integral and changing the PMF to PDF, we have expectation of g of x. So g of x is a function of x, right? So we put gx here, and then the PDF. So this is the PDF. Okay, so remember that in general, the PDF is denoted by fx and PMF is denoted by px. Okay, so and also due to the linearity of the expectation, we have expectation of ax plus b is a times expectation of x plus b. So this is due to the linearity because e is a linear function. Okay, and due to linearity itself, like we can by induction we can also say that e of x1 plus x2 plus dot 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 xn can be written as e of x1 plus e of x2 and so on. So let us see an example of computing expectation of a function of random variable. So let us say our function gx is some x to the n, where n is some natural number. Okay, so here this is our g of x here now, and the goal is to compute the expectation of g of x. Okay, so what we will apply the formula directly, right? So expectation of so the expectation of g of x, right? So which is xn, right? So expectation of g of which is expectation of x to the n, and this is a continuous case. So this is the continuous case. So we have minus infinity to infinity and xn. Okay, so it's like gx, right? So here we have gx is x to the n. So this is like small x to the n, and then the PDF of that. So fx x dx. So PDF is already given to us. Okay, so PDF is given. So this is given. So this will be integral of minus infinity to infinity, and well, do we need really minus infinity to infinity? Because if you see the values for which it's taking positive values only between 0 and 1. So it is enough that we restrict our domain to 0 and 1, because other integral will be anyway 0. So I substitute minus infinity to infinity by just 0 to 1 by looking at the range of x. Okay, and then other things remain same. So xn, and then PDF we substitute here. So this is x plus half. Okay, and then this is dx. And if we integrate this, so if we integrate this, then we get, so the first term is xn plus 1. So integration of xn plus 1 is x to the n plus 2 by n plus 2. Okay, and then the second term is half of x to the n. So this is like half, and then xn plus 1 by n plus 1. This is the integral, and then 0 to 1. So if we put these values, then it will be how much? In place of x, we put 1, right? So if we put 1, then it is 1 by n plus 2. Okay, so here let me work out. So 1 by n plus 2 plus 1 by 2 n plus 1, and then minus, and all other will be 0. Okay, minus 0 terms. Okay, so if we do this, then this is 2 n plus 1 and n plus 2, and then on the top we have 3n plus 4. Okay, so that's the answer. So we can compute from this example, the takeaway is that we can compute expectation of a function of a random variable. Okay, that's what we did here. The function was gx, which is x to the n, the power of the random variable. Okay, so that's an example. Now let us see variance of a continuous random variable. Variance, remember that it was defined as expectation of x minus mu x whole squared. Okay, in other words, it is the another way to say is that it is the second central moment. Okay, so remember this is the second central moment, and due to linearity of E, we can also write it like this. Okay, so this is the derivation we have seen before. So for a continuous case now, we have variance of x is the same formula here, but it's just that the expectation computation changes, right? So in the discrete case, we have summations, but here we have integral. So it will be integral minus infinity to infinity, x minus mu. So this is the function of some random variable gx, right? So this is the value gx here. Okay, and then the PDF of x. Okay, so that's how we compute expectation of gx is x minus mu x whole square and then PDF of x. Now, so another way is to write like this. So if we write like this, then expectation of x square minus expectation of x whole squared. So in that form, in the continuous case, it will look like this. Expectation of x square is x square PDF of x minus expectation of x whole square is mu x square. Okay, so that's the notation for expectation of x. Mu x is the notation for expectation of x. We have seen this before. So this is how we compute variance. Okay, in the continuous case. We also recall, because we have seen this before, this also holds in the continuous case. Okay, so variance of ax plus b will be a squared. So the constant that will come out will be squared. Okay, in other words, variance is not necessarily a linear function. Okay, the constant comes out as a square, and the constant that you add has no effect on the variance. Okay, so shifting your random variable by some constant has no effect. Okay, in other words, variance of, let us say, x plus 100 is same as variance of x. Remember, variance denotes the spread of the data. Okay, so if I just translate the data by 100, it doesn't affect the spread of the data. The pattern of the spread is the same. Okay, so variance computes the spread of the data about the mean. Okay, so about the mean, how the data is spread out. Okay, so what is the expected value of the random variable subtracted about the mean. So this gives you a nature of the variance. Okay, and we have the square term as well. Okay, so more the spread, more the variance. Okay, so that's how the square will be. So more you're far away from the mean, that number will be squared a lot, right? So more far you are from the mean, the more it will contribute to the variance. Okay, so so more variance means your data is more spread out and so on. Okay. Okay, so consider the PDF of the continuous random variable, which is this. Okay, and so in this case, like, let us compute variance of this. Okay, so we have discussed variance, so let us find the variance. So find mean and variance of the random variable x, whose PDF is given by this. So expectation of x is we know it's minus infinity to infinity x times PDF of x dx. Okay, so this, now we know that x range, so range of x is starting from 1, so closed 1, and it goes up to infinity. Okay, so infinity, it's always open. Okay, because infinity is not part of the real number, right? So it's always open. Okay, so minus infinity infinity now does just boils down to 1 to infinity. Okay, and 3 by um, it should be 3 by x to the 4, I guess. I think we have to check whether this is a valid PMF. Okay, so let us check whether this is a valid PMF. If it is a valid PMF, is not PMF but the PDF, is PDF valid? I have a doubt that there may be, whether it's 3 or 4, I'm not sure here in the denominator. So to fix that, I may do a test. So that test is minus infinity to infinity. So fx x dx, that must be 1. That's what we want for a valid PDF. Okay. In fact, any function that satisfies this minus infinity to infinity is some corresponding to this, there is some random variable and for which this is the PDF. Okay, so that's the requirement of a random variable. Okay, so in this case, let us check this, right? So minus infinity to infinity. So in this case, it's like 1 to infinity, 1 to infinity, because that's where it's defined. So 3 by x to the 4. So what is this? So 3 comes out. Okay, and then we have x to the minus 4, right? So x to the minus 4 integration is what? Minus 4 plus 1 divided by minus 4 plus 1. Okay, so this is x to the minus 3 by minus 3, right? So this seems to be correct, I think. So minus 3 comes out, right? And x to the minus 3, and the integration limits are this. So this goes, is a minus 1 is left out here, and this is like infinity, so it's like a minus 1 and then 0 minus 1. So this comes out to be 1. So I am sure now that it is indeed x to the 4 here, because x to the 3 may not have worked here. Okay, so that's how I verified that this is a valid PMF. So now I will continue with this, assuming that this is correct. So x fx is 1 to infinity and 3 by x to the 4 dx. Okay, so this is how much? Okay, so 3 comes out, and then I have x to the 4 here, right? Okay.
So you should have multiplied by x.
Yeah, I should have multiplied by x. You're right. Yes. So this will be 3 comes out, and then I have 1 to infinity. So expectation, don't forget to multiply by this x here. Okay, for the expectation of x. If you are computing gx, then you have to multiply by gx. Okay, g of x. Okay, so this is like 1 by x cubed dx. Okay, and this will come out to be minus 3 by 2 x minus 2, right? And then 1 to infinity, and this will be 3 by 2. So this is the expectation of x, and then if we compute the other part, so the expectation of x square is minus infinity to infinity, and then x square fx x dx, and this is integral 1 to infinity and 3 by x square dx, and this is equal to minus 3 x inverse 1 to infinity, and this will come out to be just 3. Okay, and then variance of x is expectation of x square, remember, minus expectation of x whole squared. Okay, so we have these two terms. We have deliberately computed x square and this, so that we can compute the variance. So this is 3 minus 3 by 2 whole square, which is 9 by 4. So which is 3 by 4. Okay, so this is the variance example of computing the variance of a random variable. So Now let us look into this example where X is a uniform. So remember uniform distribution, how it looks like. Okay, so and then let y be some function of x. In this case is exponential of x. Then the question is find the CDF of y. So find the cumulative distribution function of y and find the PDF of y and find the expectation of y. Find the mean and variance of x as well. Okay, so let us see an example let us see how we can solve this. Okay, so so what do we have in hand? We have the uniform distribution. So we are given that x is a uniform distribution with the parameters 0 and 1. So this means that the CDF is known to us. So what is the CDF in this case? In this case, the CDF is 0 for x less than 0 and x for 0 less than equal to x less than equal to 1, and it will be 1 is the CDF here, capital F, right? So for x greater than 1. Okay, so this is the CDF of x, right? We know this for the uniform distribution with parameter 0 and 1, and the corresponding PDF. So corresponding PDF is obtained by, so this is like a small xx is, so it remains 0 for the cases, but we have to differentiate, right? So between 0 and 1, so that will be 1 for 0 less than equal to x less than equal to 1, and it is 0 otherwise. Because for this part differentiation will be 0, for this part differentiation will be 0. So this is our PDF, okay, and this is our CDF. So these are the two things we are given, and from there we are supposed to find the CDF of y. Okay, so and what are the other things we notice? Remember the range of x is where? Remember that we redefined the range. Okay, so you can say that technically the range is like 0 to, so the range of x, you may argue that it's from like minus infinity to infinity. It is defined, right? Because it's defined for all values of x, especially like if you look at the PDF. Okay, but remember in the last class we said that we redefine the range as only those part of the interval where PDF is like greater than 0. Okay, remember that we redefine the range to be set of all x such that fx x is greater than 0, because any place other than these is where fx is 0, because fx is always greater than equal to 0. So only possibility is either greater than 0 or equal to 0. So the places where it's equal to 0 is not really useful for a computation point of view. Okay, whether we want to compute probability or whatever. So we redefine the range to be like this, remember, where this is greater than. So we from here we see that the range of x is actually between 0 and 1. Okay, so we can say that range of x is actually between 0 and 1. And with this, the range of y, which is exponential of x. So y will be defined only on these values. So range of y will be, now with this range of y will be 1 comma e. Okay. So with this we have range of x, range of y. And now we want to compute the PDF of y. So let us compute the PDF of y. So let us compute the CDF. Okay, so CDF of y, CDF of the random variable y, and the CDF of a random variable y is fy y, which is probability that y is less than equal to y. Okay, and we know that this is 0 for y less than 1. Okay, so and because that's how the range is, right? So and then fy is 1 for y greater than equal to e. Okay, because that's the range of y. So CDF will be 0 for y less than equal to the lower endpoint of your range, and then upper endpoint of the range, it's going to be always 1. That's the property of CDF. Now to find fyy for the range of y, we have fyy is probability that y less than equal to y, which is probability that, so y is what, e to the x less than equal to y, right? Now this is equal to, now I can take a log without changing the inequality because log is a increasing function. Okay, so I can write this as probability that that x is less than equal to natural logarithm of y. Okay, I will take natural logarithm so that e like goes away. Okay, so this is this, and then we know from the uniform distribution the probability that x less than equal to log y. So we know that from the uniform distribution, because x follows the uniform distribution. So for those values of x that lies between 0 and 1, in other words, like those values of y which lies between 1 and e. So okay, so for those values, it's going to be just ln y itself, because that's the uniform. The uniform distribution is just x. Okay, that's the same as the argument you are talking about, right? So that's the uniform distribution. So hence this will be equal to fx of L natural logarithm of y. Okay. Okay, this is the same thing as asking for fx ln y, but fx ln y is nothing but just ln y. Okay, that's fx for uniform. Fx of the argument is the same as this within 0 and 1 interval. Okay, so this is what we have because 0 less than equal to natural logarithm of y is less than equal to 1 for y in the range 1e. Okay, so since ln y lies between 0 and 1, fx ln y will be ln y because fx is a uniform distribution. Okay, now so we can summarize this. So it's always good to summarize in one place. So the CDF is 0 for y less than 1. It is natural logarithm of y for 1 less than equal to y less than e, and it is 1 for y greater than equal to e. Okay, so we can wrap up this so this is the CDF of y. Okay, so now we can also talk about, we are interested in the PDF of y. Okay, so for the PDF of y, PDF of y, we just need to differentiate this. We know that PDF is a differentiation, right? So this is fy y is fy prime y, and this is 1 by y for 1 less than equal to y less than equal to e, and 0 otherwise. Okay, so we just differentiated this part. Okay, and other places it will be 0, so that's the 0 otherwise. So we got the PDF also. Now we compute the expectation of y. Expectation of y is expectation of e to the x, because that's how this is defined. So this is easy. So this is fx dx. So this is and so this was like minus infinity to infinity, but then we know that the PDF is defined only for bit 0 and 1 range. So it boils down to only the range and e to the x. So between 0 and 1, and we are computing the expectation of x. So what is the PDF of x? The PDF of x was 1, right? You remember the PDF of x is 1. We need the PDF now, not the CDF, right? So PDF for x between 0 and 1 was 1. So here it's 1. Okay, between 0 and 1, the PDF is 1. So this is dx. And this will come out to be how much? So e to the x integration is just e to the x. Okay, so it is like e to the x 0 to 1. So e to the 1 minus e to the 0, e minus 1. Okay, that's the answer we have. Okay, so we could have found expectation of y also via the PDF of y. So here what we did is that we transferred to the x and then we solved our problem in the x domain. But we could have used the PDF of y itself, because we have computed that, right? So this will be y and then the PDF of y dy. So this is now the valid range of y was 1e. So here we have to put the correct range and y, and then the PDF of y that we computed was this. Okay, so 1 over y in this range dy. So this is like 1, and then it's like e minus 1. Okay, so we could have also computed a PDF like this. Okay, so we can think of some example like this. So let us say that x is uniform. Okay, x is uniform between 0 and minus 1 and 1. Remember this thing changed here now. Okay, range is changed, and y is x square. Then find the CDF and PDF of y. Okay, so find the CDF and PDF of y. Now, what is the range of x? Range of x is given by this uniform limits itself, so which are minus 1 and 1. Range of y are the square of the x values. So this will, I mean, square of the x values, or like whatever values your x is taking, right? So they will get like squared. So the negative terms will go away. 0 to minus 1 is no longer relevant here. So range of y becomes 0 to 1. And because this is a like x square here, and to compute the fy of y, which is probability that y is less than equal to y, which is equal to probability that y is x square. So x square is less than equal to y, and this is the same thing as saying that probability that minus square root y is less than equal to x less than equal to square root of y. Okay, so that's the same thing. And since this is uniform now, okay, because this is so the random variable is now bounded between some x and some lower end of x and some upper end of y, and then we are, and this is like x ranges, and we know that it follows a uniform distribution. Okay, so this will be proportional to the interval, right? So we remember for the uniform case, a less than equal to x less than equal to b, the probability was how much, right? So this was like or let us say like c less than equal to d, and x was uniform AB, then remember the probability computed was d minus c by a minus b. Okay, so that's what we are going to do here. So this is square root of y minus of square root of y divided by, and the original range is 1 minus 1. Okay, the a and b here are 1, minus 1 and 1 respectively, and so this is like square root of y. Okay, so that's the PDF, and if we have to compute the, I mean, this is the CDF of y. So CDF of y we can now summarize. So summarize. So FYY is 0 for y less than 0, and it is square root of y. That's we just computed for 0 less than equal to y less than equal to 1, and it will be 1 for y greater than equal to greater than the outer limit. Now we know that CDF is continuous case, in this case continuous and differentiable. I mean differentiable in the cases, in the ranges where we need, not on the corner, right? Okay, so if that is the case, then we can obtain that small y, which is the PDF now. So PDF of y can be computed by differentiating the CDF. So if you differentiate the CDF in the range where it is except the corner point, which are 0 and 1, then it is 1 by 2 square root of y. So the differentiation of square root of y is 1 by 2 square root of y for 0 less than equal to y less than equal to 1, and it is 0 otherwise. Okay, because differentiation of 0 is 0, differentiation of 1 is 1. Sorry, 0. Okay, so that's the PDF y, and that solves this question. Okay, so now so there is something called method of transform, and method of transform is a formula to compute the PDF in a faster way, but it has some requirements. Okay, so now we want to discuss something called method of transform. So let us say, and this applies to function of a random variable. Okay, so given a random variable and then given a function of a random variable, given the PDF of a random variable x, how can you quickly obtain a PDF of a function of the random variable? In other words, PDF of y equals to g of x. So this can be applied, but let us build step by step. So it's the first step is like the simplest form is like when g is satisfying the following conditions, like g is differentiable. So that's the first criteria you need. And g is a strictly increasing function. Okay, you can already say that this is a lot of restriction because not all functions are strictly increasing. But let us build step by step. I can say that this can be generalized further. Okay, it can be generalized to cases where it's not necessarily always strictly increasing or always strictly decreasing. Okay, idea will be to partition interval in the cases where it's strictly increasing, and then other interval where it's strictly decreasing, and so on. So first let us start with a strictly increasing case, and then we will do a strictly decreasing case, and then we can partition the interval into increasing, because functions can be partitioned like that. In general, we can do it, right? We may not do it for functions that oscillate too much and so on, but it may not be convenient to do that, but in general we can do. Okay, let us see this. So strictly increasing, what is the meaning of strictly increasing? If x1 less than x2, then gx1 is less than gx2. That's the meaning of strictly increasing. Okay, so the graph of the strictly increasing function is like this. Okay, or like this. It doesn't necessarily have to be linear. Okay, but the point is like if x2 is greater than x1, then fx1 is greater than fx2. Okay, so fx1 is greater than fx2, higher than fx2. fx2 is higher than fx1, I mean. Okay, so in this case, the claim is that we can directly find the PDF of y using this formula. Okay, so you can directly write the PDF. So what does this mean? So this is like fx x1 and then g prime x1. Okay, and this is same thing as saying fx x1 and then d x1 by dy, where gx1 is y. Okay, so wherever like gx1 is y, we can write like this, and then it is 0 otherwise. Okay, if gx equals to y does not have any solution, okay, then then we define it to be 0. Okay, so this looks a bit cryptic right now. Okay, so this looks a bit cryptic, but let us try to prove this, and when we prove this, then we will see the reason behind all these conditions that we have we are imposing. Okay, so we have like 6 minutes, so let us see. So since G is strictly increasing, G inverse is well defined. Okay, is well defined. In other words, G inverse exists, right? Because for a strictly increasing, in other words, for a monotone, strictly increasing or decreasing, it's well defined. So for each y in the range of x, there exists a unique x1 such that g of x1 is equal to y. Okay, so remember G G is a function, right? So G is a function that's taking going from like a range of x to a range of y, and G inverse will be range of y to range of x. Okay, so for each y in Rx, there exists a unique x1 such that gx1 will be y. Okay, it should not be Rx, it should be Ry. Okay, so each y in Ry, there will exist an x1 such that gx1 is y. Okay, that's what it's trying to say. So so in other words, we can also write x1 is g inverse y. Without any ambiguity, we can write x1 is g inverse y, because g is like strictly increasing. So strictly increasing means it's 1 1 and on 2. So so x1 is equal to g inverse y. Okay, so in general, we may not be able to write. Okay, so so fyy is P of probability that y is less than or equal to y, probability that y is g of x is less than or equal to y, is equal to probability that x is less than or equal to g inverse y. Okay, so the inequality does not change, right? So I can apply the g inverse on the both sides, and then I will have x less than or equal to g inverse y, and that's coming because it's g is monotone, right? Right. So you are okay with this? I can write like this. If g of x is less than or equal to y, then so what does this mean graphically, right? So g of x is less, or y is greater than or equal to g of x, right? So it's like this. Okay, not like this, but it's like strictly increasing, right? So g of y is here, right? Y is greater than or equal to g of x. Okay, so here let us say this is x. Okay, and this is g inverse y. We know because the inverse exists, so this will map to this. So if y is greater than or equal to g of x, which is here, and since this is like increasing function, it must be that x is less than equal to g inverse, or other way to say is like g inverse y is greater than or equal to x. Okay, so this must be greater than or equal to this. If this is coming because of the monotonicity, right? Okay. So, okay, I'm already like, okay. So what I will do is that I will leave up to here. So this is fx and g inverse y. Fx of g inverse y. That's how the CDF is defined, right? So x less than equal to this is the CDF of g inverse y. And we will continue from here in the next class. So now next step will be to take the derivative to find the PDF. And once you take the derivative, you will get the result in the theorem. Okay, you just have to take now d by dy. Okay, because this is like eventually this is seen as a function of y. Okay, now you take the derivative by dy, and if you do the derivative, you will get the answer. Now the next steps are what will happen for the strictly decreasing case. Now you can take this proof for the strictly decreasing case, and you will find out some result there. And then a more general result is function can be increasing, decreasing, but we will partition it into increasing and decreasing cases. And we apply the theorem piecewise. Okay, so we will apply this, we will get the PDF in piecewise in a strictly increasing part, decreasing part, increasing part, and so on. So that's how we can actually compute PDF in the general case. So that will be our goal in the next class, a method of transform, and then some examples on this. And then we will go to some special distributions. So we have seen distributions in the discrete case. Now there are distributions in the continuous case. So we have seen distributions like Bernoulli, binomial, Poisson, geometric, and so on, right? Uniform. Now we have already seen uniform in the continuous case, and we will see distributions in the